Okay, so last week we have studied unsupervised learning. Unsupervised referring to a learning method in which we do not have any label. So what we did, we just cluster them or group them based on the content, right? So we could have 2 or 3 cluster. Okay, so when we compare with the supervised learning is a task that where we perform classification. We classify the record or the item based on the label that we have. So if we compare with the clustering, if we look at the diagram here, clustering is simply a segmentation task where we try to group or cluster them based on the content or based on the characteristic of the data. In comparison to supervised learning, we have a label or we have a direction or guideline that we need to train the model. Okay, so for this one, for the clustering, we don't need to train. No need to train, we just simply perform the segmentation. For this one, we have a guideline or something to refer to. So for example, like for classification, we have label. So each of our data have label. So given a new data here, we know what is the first label because they are nearer to the red one, the red triangle. So basically, we try to classify them based on the reference of other label or other item. Similar to regression, I think this one you will learn in the second part of the regression, in which we try to draw a line that will minimize the differences between the line here to the actual data that you have. So we try to minimize the error. And the line will be the model that represent your data. This is in regression. So this is when you want to forecast numerical value. And for classification, this is used for categorical value or label. So these are the three main types of machine learning. So we have done this one. We study the k-means and also the DB scan, right? Okay. In classification, we start with the binary classification because we have 2 classes. Okay, we start with the 2 classes, but later on when we have more than 2, they call it multi-class classification. So in binary classification, we only have 2 class instance, 2 sample classes. When we compare with multi-class classification, we have multiple class labels. So in this case, we have more than 2, which is 3. Okay. So the number of classifier models depends on the classification technique that we apply to. So for example, this one for the binary, we need to have a model. We can split them into 2. So this one we only need 1 classifier. For this one we have 3 lines that can separate them. So in this case we need to have our model 3 classifier because we have 3 lines. Okay, 3 lines that separate all the 3 classes. When you form the classification, you will not see or they will not show you the step-by-step on how they perform classification. They just give you the result of the classification. So what are the processes involved in classification? Firstly, we have the raw data here. Then we will perform the data preparation. This one we select data which is complete, and then sometimes we need to normalize them. When we say normalize, we want to have the range of value between the range of value of the attribute um, not big compared to the other column. For example salary, and also the age. So when you want to normalize them, for example, this is 15,000, this is 100, and then we also have 100,000. Okay, but for the age we only have 37, and then 25, 50. So when look at the salary and age, the salary has large compared to the age. So when we have this kind of differences, we need to normalize them. So meaning that we will perform like scaling or normalization. Later on, I'll show you how we can perform the scaling or the normalization. So we want to have the differences between these two not that far. So that is the data normalization. Sometimes we need to construct the features based on data that we have. So this is like a feature construction, feature selection. And this one we select the row. Okay? This one we select the column. Okay. So once we perform the data preparation phase, then the data will be divided into training and testing data. So what happens is that the train data will be used to train the model. So this is the model that we have. Okay, they go to this phase, the learning phase, and then the classifier said, okay, show me the example of all the record that you have together with the label so that I know what to learn. This classifier said, teach me, they will learn by themselves, they will observe the data that they have, and based on the training data, they will be ready. So when they are ready, when they are here, okay, they said, I'm ready to form the prediction. So we will test them using the test data we have here. Then we will test the model here. Then we look at the accuracy that they have here. Okay. So we'll continue training them, feeding them with new data, and then try to improve the prediction here until we satisfy with the output. Then we have the final model. So this can be used to perform the classification for new item. So this slide, three things that we need to know. First, we need to prepare the data. So 80% of the time you'll be busy preparing your data. Okay, how to feed into the R software, and then how do you clean them and so on. Okay, once you clean them, you divide them into training and testing. So that the train data will be used to train the classifier. And then once you finish with the training session or training phase, then you will use the test data to test them, how accurate they are. Once you okay with the performance, then you have the final model. Okay, so these are all the processes involved in the classification technique. Okay, but we want to know what happened here, how they learn, how the classifier learn from the data that we have. So for example, we say, okay, we have a compact car, we have family car, but how do you extract the feature that say that, okay, this is family car? Okay. For example, is car X a family car? So what do people expect from a family car? So we gather the information, maybe we buat fieldwork to perform the survey. So we ask them few things. What are the uh, characteristic of a family car? Okay. Some people look at the size of the car or the fuel consumption, or the capacity the engine capacity of the car, and so on. Okay. And the output is, we want to say whether they are a family car or not family car. So positive will be family car and not family car. So the input could be a few things, maybe price, engine power, seats capacity, and many more. In this example, we use the price and also the engine power. Okay, so it depends on what data you have. So in this case, we have two variables. Okay, so let's plot them and give some example. For example, we have the price here, the x-axis, or engine power, the y-axis. So for each instant that we have, we represent them using price and also the engine power. So we have this training set. The whole thing is called the training set X. And for each of the sample that we have, they have their own label. So if they are positive, they are 1. If they are not positive, they are 0. So over here we have a sample of 1 to n. So n here refer to number of sample that you have. Okay? And the X refer to individual sample that you have in your training set, and then the R is the label. So you have the input and you have the label. So the T referring to item ID or item number what. So as you can see, based on the layout of the space here, so this is the area that we are looking. So we could say that, okay, this is the area where all the samples are positive. So if we look at this one, so we could say that if the price is fall within P1 and P2, and the engine power is within E1 and E2, so we could say that that is the as positive for C. Okay, but the classifier will have to learn that. This is based on our perception, but maybe the model learn and they say, okay, maybe model learn this one. This area will be the class. So different area here. The red one is what the assumption made by the model. But we, as human being, okay, we claim that, okay, the blue rectangle is the positive one. So if I go to the next one, so the yellow one is the assumption made by the classifier, and the blue one is what we the actual space for the class. Okay, so for example here, all the sample that fall within the blue, call it positive. Huh? For example, if the sample is here, okay, the model say the assumptions, they made an assumption that X is positive, right? Because they fall within the yellow rectangle. But they are not actually positive because they fall outside the blue. So based on the classifier, they say that that is positive, but actually they are not. So this is what we call the false positive. According to the model, they are positive because they fall within the yellow. In based on the blue rectangle, they are not. So that is false positive. What if data fall here? So based on the blue one, they are positive, right? Based on the classifier itself, they assume that X is negative. So that is wrong. So that is what we call the false negative. So the error that made by the classifier, this is what we want to measure. Number of sample that are false within this area. How many of them are false in this area? This one are they have contradict assumption between the model and also the actual one. So basically, given the input that we have, we look at the number of error in which the area covered by the actual class, not the same with the assumption made by the classifier. So this is, in this case, we have two number of error. So this is what we want to look at here, because the light blue one is the smallest area that the classifier can assume. So that is what we call the most specific hypothesis, a most specific assumption made by the classifier. Or we could have the blue one, the light blue one, yang outside ni. It is the most general hypothesis because they cover a larger area compared to the actual one. Okay, so this is what we call the actual one. So the space between the specific and the G1 is called the function space. We have to know how much to move the boundary so that we can cover the actual class here. Okay, and if you look at this one, that is the margin. So choose edge with the largest margin. Largest margin meaning that we the middle one. Okay. So what happened in the learning process in which the assumption made by the classifier will be different from the actual one. So what they did, they will try to make the maximum, try to find the largest margin between the specific and also the general assumption. So they take in the middle. Okay. So that's how they optimize the classification. Okay, and these are some of the that algorithm. So we will look into this first. So we will look into this. So this is the easiest method that everybody can learn. Okay, so k nearest neighbor. So k here refer to the number of nearest neighbor that we are looking at. Any question? Everything's okay?
Okay, dokter.
Okay. So we will look into this nearest neighbor. So basically, based on the diagram there, we have two classes A and B. So when we given a point, the black dot there, so if we look at the k equal to 5, meaning that the nearest 5 neighbor, so we can see that the square blue is the majority one. So that reason we assign the black dot as the belong to the square blue. But if we look at k equal to 10, we have majority symbol is this triangle red. So the black dot will be labeled as red triangle. Okay, so it depends on k. Okay. So for this session, you will look at the definition of nearest neighbor classifier, and then how do we measure the similarity between two examples using distance, and how do we apply this KNN in classification. Okay, so like I mentioned just now, we will look at the nearest neighbor. So what is nearest neighbor? Nearest neighbor classifier are defined by their characteristic of classifying unlabeled example by assigning the class of similar label example. So for example, like this, if k equal to 3, so the majority will be the green triangle. But if we take k equal to 7, which means the 7 nearest neighbor, so majority will be star, red star. So the new example will be classified as the red star here because majority of them are star symbol if k equal to 7. If k equal to 3, majority will be the triangle. So that is the basic assumption of k nearest neighbor. So how actually we apply this algorithm? So for example, here we have data about the sweetness, the crunchiness. So we have all the fruits here, and we have the label here. So this is the type, and we have this. So if we plot them in this graph, we can see all of them here. Then we can group them based on the value of sweetness and crunchiness here. So if we have this tomato or a new item here, how do we measure the distance between this new tomato to the other label? So are we going to classify them as fruits or vegetables or protein? Okay. So there is a way on how we can measure the distance. So that's why we look at the formula here at the moment. How do we apply them? So the distance method that we use, we call it Euclidean distance. So the Euclidean distance will take the differences between the value of the vector of each sample, and then you take the square, sum up all of them, and then you take the square root. Okay, we take the square because we want to eliminate any negative value, and then we add them together because we want to accumulate the number of differences. And then we take the square here, just a square root here, just to reduce the value. Okay. So for example, suppose we have the tomato, the sweetness is 6 and the crunchiness is 4. Okay. And the green bean, the sweetness is 3 and crunchiness is 7. Okay. So if you want to take the difference between the tomato and the green bean, okay, So what we do, we the 6 minus 3, okay? 6 minus 3, and then 4 minus 7. And we take the square, and then we add up them together, we take the square root, and this is the value that we get. So we'll do for the rest of the ingredient or the fruits that we have, so like the grape, nuts, orange, and we look at the distance here. So if k equal to 1, which means we take the nearest one, only one sample or one nearest neighbor, we will classify them as fruits because this is the nearest one. If we take k equal to 3, so that means this is the first one, the second one, and then this is the third one. So the majority is fruits. So we classify tomato as fruits. So do k equal to 2 because sometimes you have 1, or you take 4 or number genap. So you have a similar split of 2 or 3, 3. So it's recommended to value k as the odd number. So that is how we measure the distance. So that's why they call it k nearest neighbor. K refers to the number of nearest neighbor that you want to consider. And we use this equivalent distance to measure the distance between the new sample to the sample that you have in your data set. So they call it lazy learning because you do not have to model them. You just have to measure the distance. Okay, this is how they perform the classification. But before we can perform the classification, if you look at the value of this and this, the range are more or less the same. So that is fine. When we go back to the example that we have previously, when we use salary and also age, when we perform this inclusion distance, the salary tend to have more bias because they have large value. So the differences between the salary of one person to the other person might be bigger compared to the age. So we do not want to have such imbalance bias. So what we do, we perform the normalization. Okay. So in the normalization, we have this min-max normalization or the z-score. So what happened here is that we will normalize them between 0 and 1. So this is between 0 and 1. The range will be 0 and 1. And this one negative 1 to 1 or more. Okay? So we will try to reduce the value, normalize the value. Let me give you an example here. How they are applied. So for example, if we have the salary here, and then this is the first person, second, third, and fourth. So 1,000 and 500, 100, and then 10,000. Okay. So, and then we have the erase that one. Okay. And also we have age. 1, 2, 3, 4. So this is 50, 25, 22, 35. So if we take the differences between person number person number 2 and 4, there will be a lot of differences here. So when we take the square, the value will be big. So we want to normalize this. So how do we use this min-max? So we have the x here. And then what is the minimum value here? Minimum value is 100. Divided by what is the maximum? Maximum is 10,000 and minus 100. So for each of the value here, for example, for this one, so we plug in the 1000 to here, so we will have 1000 minus 100, and this one will be 9900. So if we compute this one, we will get, let me calculate. So the value will be 900 divided by 9900. So what you get is 0.09. So this value will be used to replace this one. So if we take this value and then we say, okay, the value of x is 10,000 minus 100, and then you divide by 10,000 minus 100. So this one will give you 1. So this one will be replaced by 1. If you take this one, the value here will be 100. Okay? So 100 minus 100, this one will be 0. This one is 0.09. So this one will fall within the range of 0 and 1. So notice that if you take the min-max normalization, the value of your feature will be normalized to between 0 and 1. So you will perform similar to this. For example, this one, maximum is 50, minimum is 22, and x is minus 22 on this formula. Yeah? So for each of this value, you put 50 here, and then you get 1. This is 1. If you put 22 here, this one will become 0. So if you put this one is 25, so 25 minus 22, you get 3 divided by 28. So this one will be 0.11. Okay, so this is 0.11. Okay, so that's how we use the min-max normalization. Okay, so similar to this, we use the mean and also the standard deviation. Later on, we show you how do we use this one min-max normalization. Okay, so this is important. So before we can feed our data into the classifier, we need to normalize them. For categorical value, if the value are the same, we say they are 1. If they are not the same, they are 0. Because this is a numerical value. But for categorical value, we just use 1 and 0 only. Okay. So when we have an algorithm, they call it this is lazy because we do not need to train. So what we did, we just measure the distance. We use the formula to look at who are the nearest member to this new guy. And then we will label them based on the majority label that we have for the nearest neighbor. So basically, we are looking at the distance only. So They also call it as instant-based learning or rote learning. Okay, they do not build a model, they don't train a model, but they use the distance method to determine the label. Okay, so the idea of classification in KNN is based on the distance. So let's take a look and how we can apply this one in the breast cancer classification. So in this example, we have 32 features, 32 variables, and we have 569 examples. So this is number of rows, okay? So in the feature, one feature is the ID. So we will remove this one because the ID number does not contribute to the class label. And also have the class label. So this is the label called cancer diagnosis. And we only have 30 because we minus this one, we only have 30. So how does the data looks like? So I will share the data later on. So this is how we read the data. So the data is saved as Wisconsin breast cancer data. So they are comma separated vector data. So we use the read.csv, and the string as vector is false, meaning that all the string will be read as a string of character. Okay, so you can see here when we manage to read them, and then we look at the structure of the data, how we have character here. Okay, so this is a character that determine the type of breast cancer that we have. So we have B and M, benign and malignant, two types of classification, and we have all this number. So we use all this number to form the classification. So we do not need the ID here. So in that case, we will remove the first one, first column. So we will drop that one. So if we look at the structure again after removing the first column, now we only have 31. 31 is 6 observation. Okay. We could also look at the content of the table. So we can see, okay, this is the data that we have. We focus on this column. So in our sample, we have 357 number of B types and 212 number of M types. Okay, so this one just tell you how many belong to B types, benign, and how many belong to malignant. And these are the type that we have, meaning that the first one to 7 1 belong to B types, and the 8th one belong to the malignant M. Okay, so what happened here is want to change them to a character. So to the label, the character change to label. Okay, so this is part of the data pre-processing. We prepare the data. So do we perform them? So we say, okay, we will perform the factor. We will change this character into symbol, to benign and also malignant according to this order. So B will be changed to this one and M will be changed to this one. So now when we have converted them into label by using the factor here. So when we try to look at the content again, so all them will have the label value. So once we settle the label, then we can also look at how many percentage of data belong to the first type and also the second type. So we use the proportion table based on the label that we have. Then we round them to one digit. One tick per puluhan. And over here we know that 63% of the data belong to benign label and 37% belong to malignant label. Okay, we could also perform the descriptive statistics. So we just type summary, and then we look at the radius, the area mean, and the smoothness. So this is just the three attribute that we have out of the 30. So we just want to look at this, the first three. So this is how we perform the descriptive statistics. We use summary. Okay, so if you look at the range of the radius mean, the area mean, and also the smoothness, this is very small. This is very big, and this is in between. So remember, now when I say when you have large value, you will have more bias on the output of the classification. If you have small number, they have less bias. So that's why we need to perform the data normalization. We have to normalize this. So how do we perform the data normalization? Okay, so we use the this function normalize. So we say okay, we will use the same formula just now too. We use the x will be passed to the function, and then we will say x minus mean divided by max divided by minus mean. So this is the formula that we saw just now. So we have this function now. So when we have to normalize this range of value, they will give you this value. So notice that the range of value falls within 0 and 1. As similar to here. So this is just to verify that the normalization function is okay. So this is how we define the function, and then we want to apply that particular function. This is the function that we want to use, and we want to normalize all the value that we get from column 2 up to 31. So basically we have 30 column. So we will apply this function to this data, and now when we perform the mean for the area mean. So notice that the minimum value is 0, maximum is 1. I compare with the area mean just now. So this one becomes 0, this one become 1 already. So that means we have normalized them. So we normalize them using the function that we define using min max, and we apply it to all data. Okay, next. We finished with the data preparation. Okay, now we want to divide them into training and testing. So what happened is that, okay, I will take the first row up to 461 row. So that means row number 1 sampai row 469 will be used for training. And then starting from row number 470 until 569. So this one will be used for testing. let me write that one. So 469 will be used for training, and then 470 up to 569 will be used to testing. Okay, so this number of row is up to you. You want to have 1 to 300 or 1 to 500. Make sure the remaining data is used for the testing. And we also we also extract the label for the trend. So this is the first column. Okay, so we will take the label for all this data from 1 to 469 to 1 to 469, and then we take the label. So basically here we keep the label of the training data, and this is the label for the testing. Okay, how do we call the KNN or the K nearest neighbor? So basically this is the format. We call the model KNN, and we feed them with the training dataset and also the test dataset. And these are the class label that we use. And what is the value for K? So for example here, call the KNN, and we feed them with the training dataset and also the test dataset. So basically we have this model KNN. So we feed them with the training dataset. Okay, once they are trained, this is KNN. They already learned the data. So next we will feed them with the test. So based on the test, we will know the accuracy. This is the value of the accuracy. So that's why here we look at the training dataset and also the test dataset, and this is the label of your training, because we give them the train dataset with the label so that your model can learn. In this example, k equal to 21. Okay. So we could also perform a few number of k. So you could use k equal to 21 or k equal to 10 or 5. So later on you can see which one will give you the highest accuracy. So once you train them, okay, so you can perform the checking the accuracy of your prediction here. So we will, because the model that we produce here will be the prediction made for your test here. So since we feed them with the training data set, and also we ask them to do the prediction here. Okay. The output that we get here will be the prediction for this one, because they learn the data using the training data set, and then after they learn, they will perform the prediction using the test here. Okay. So we want to look at the comparison between what are the actual label and what are the predicted label. So it is for the k equal to 21. This is k equal to, so based on the name here. Okay, the name here. So what we have here is that, okay, this is the actual label that we have. So this is produced when we perform cross table between the test label and also the predicted test value. So for the benign one, we have 61 of them belong. 61 of them are predicted as benign. Okay, so this is the prediction. This is the actual one. So what we want to look at here is this and this because this is true positive and this is true negative. But we do not want to have number here because the label is malignant. They are predicted as benign. So this is okay here. So the error here is 2 divided by 100. This is the error, 2%. So the accuracy is basically total of this, so 98 divided by 100. This is the accuracy. Yeah? So this is when we use the k equal to 29. If we use k equal to 100, so we have this is the error here. So the error here, this is the error, 4%. Is the accuracy is 96%. So that's the example of how do we diagnose breast cancer. What's the time now? Let's take a break, 5 minutes. We will continue with the practical of this. I will show you step by step how do we perform this. So you can see the actual output that you will get. So let's take a break, 5 minutes. We'll continue in 15.